Hello, my name is Abhirama Subramaniam, a PhD scholar at IIT Jodhpur in the VL2G lab. Today, I'm excited to present our research titled Audiopedia, Audio QA with Knowledge. This is a joint work with Kiran from KTH Sweden and Akshat from IIT Jodhpur. Delving into the problem, speech QA or audio QA in general refers to the task of answering a question or a given audio. Consider this example where the question how many people are talking in the audio or a given audio whose transcript is shown below, and I had food at KFC last week. The system has to answer the question as one. In such traditional speech QA setting, a question has to be answered from the audio content alone. So to this end, we present a novel setting called Audiopedia, Audio QA with Knowledge. Consider a different question for the same audio. In which country was the mentioned restaurant founded? Since the question has mentioned the KFC, the answer is United States since KFC is founded in United States of America. This answer is not explicitly mentioned in the audio. However, for a system to answer the question, it has to identify the mentioned entity KFC in the audio and use the knowledge associated with the KFC to answer the question. So here, in simple terms, to answer such questions, a model requires external knowledge reasoning. And such questions which require external knowledge reasoning are referred as knowledge-intensive questions and making the task as knowledge-intensive task. So we are the first one to introduce knowledge-intensive tasks in the audio space. Under the Audiopedia, we propose three subtasks. The first subtask is single audio question answering, s-AQA. Similar to the example that we have seen earlier, s-AQA comprises knowledge-intensive questions that has to be answered over a single audio. Second subtask is multi-audio question answering, m-AQA, where a knowledge-intensive question has to be answered in the context of multiple audios. Here in this example, the question says, are the mentioned restaurants Japanese? And this question has to be answered in the context of two audios. So here in the first audio, KFC is mentioned, which is from USA, and in the second audio, Hotomoto is mentioned, which is from Japan. So hence the answer to the question, are the mentioned restaurants Japanese, is no. And the final third subtask is retrieval augmented audio question answering r-AQA, where again, knowledge intensive question has to be answered in the context of n audios. So, however, there is a catch here. Unlike the previous subtask, not every audio in the pool is relevant to answer the question. Only few are. So to solve this subtask, one has to retrieve the audio samples which are relevant from the given K audio sample pool and use only the retrieved relevant audio samples to answer the question. So in this example, for the question, how many restaurants reviewed in the podcast sell hamburgers? A system has to first retrieve the relevant audio samples, which are shown in green here, and use them to answer the question while discarding the irrelevant ones which are shown in red. Next, we discuss the dataset details. Data for all three subtasks are curated from the knowledge base provided in the text KVQA work. We first frame the data in text format and use the existing TTS frameworks to generate the audio samples. So hence, all our audio samples are synthetic. Here are the additional stats for each subtask. s-AQA has 14K samples. The answers in this subtask are open-ended. m-AQA has 500 samples. The answer in the subtask are binary either yes or no. Finally, r-AQA has 115 samples. The answers in this subtask are count-based answers 1 to 3. Further, average relevant audios per sample is 2.2 and average irrelevant audios per sample is 8.3. That means given an audio, for example, containing 10 audio samples, given a question or the context of 10 audio samples, only two questions will be relevant to answer the question, and the remaining 8 will be irrelevant and has to be discarded so that it does not tamper the answer. Further, we also propose a framework to solve the tasks such as Audiopedia. We propose a two-stage framework, AAL, Audio Entity Linking, and CALM, Knowledge Augmented Large Audio Language Model. I shall discuss these stages in detail. Starting with AEL, Audio Entity Linking Module. This module is actually responsible for identifying the mentioned named entities in the given audio and link the identified entity to its corresponding knowledge in the knowledge base. So here we make a strong assumption that given audio consists of a single entity. So let's look at how AEL works in detail. So given an audio and a knowledge base as shown in the figure, we first extract the transcript of a given audio using an off-the-shelf automated speech recognition tool Web2Web 2.0. Once we obtain the ASR text, we encode the ASR text and the knowledge base using clip text encoder and obtain their respective embeddings. Once the embeddings are obtained, we compute the cosine similarity between the ASR text embedding and the knowledge base embeddings and select the top one similar entity knowledge as the audio entity linked knowledge. The retrieved knowledge corresponds to the entity mentioned in the audio, here in this case, which is Hotomoto. So next I'll discuss the second stage in our framework, CALM, Knowledge-Augmented Large Audio Language Model. So this module leverages the AEL linked knowledge and the capabilities of LLM to answer the knowledge intensive question. This module is flexible and any modern day LLM can be adapted with this framework. Next, we discuss how CALM is adapted for each subtask of Audiopedia. First, I'll start with CALM for s-AQA. Given a knowledge intensive question over an audio, first we obtain AEL linked knowledge for the given audio. And once AEL linked knowledge is obtained, CALM framework augments the linked knowledge to the multimodal inputs of the LLM, which are the question and the audio earlier. Now the input would be question, the linked knowledge, and the audio to generate the final answer. Next, I shall discuss CALM for m-AQA. So given a knowledge-intensive question over multiple audios here in this case, we first obtain AEL linked knowledge for all the audio samples. And once AEL linked knowledge is obtained for the all audio samples, once again, CALM framework augments this linked knowledge to the multimodal inputs of the LLM to generate the final answer to the given knowledge-intensive question. So finally, I'll discuss how CALM is applied for r-AQA. So given a knowledge-intensive question in a set of n audio samples where only a few are relevant, shown in green, and the remaining ones are irrelevant, shown in red. So we first obtain ASR text of all audio samples using the automated speech recognition tool again, Web2Web 2.0 here. And once the ASR text is obtained, we encode all the obtained ASR text along with the question using a text embedded module, which is a clip text embedded module again to obtain their embeddings. And once the embeddings are obtained, we compute the cosine similarity scores for each of the ASR text embedding with that of the question embedding. And once the scores are computed, we employ a threshold criteria to choose only those samples which satisfy the criteria. So the criteria here is a threshold of 0.25. So only those samples with score greater than 0.25 are chosen as the relevant samples, while the ones that do not make the cut, we discard them as the irrelevant samples. And once the relevant samples are obtained, filtered from the pool, we employ CALM framework similar to how it is applied to m-AQA setting. That is, for each audio sampled, we perform AEL, and the AEL linked knowledge is fed to the LLM along with the question and the audio samples to obtain the final answer to the knowledge intensive question. And next, we present our framework's results over 4 open source large audio language models, namely Audio Flamingo, Gamma, LTO AS, and Quen Audio Chat. Please note that our framework does not involve any form of training, fine-tuning, or preference optimization. It is more like a prompt enhancement with additional knowledge. So as shown by these plots, our proposed framework of AEL and CALM enables the large audio language models to answer knowledge-intensive questions like the ones in the Audiopedia across all 3 subtasks. So here, the results are shown for 2 subtasks of Audiopedia, s-AQA and m-AQA. So the results say that for s-AQA, since the answers are open-ended, the zero-shot results are very poor in this case. And once our framework unexpectedly improves the open-ended answer generation for s-AQA task here. And similarly for m-AQA, our proposed framework obviously improves the performance of these LLMs. And similarly for r-AQA as well, our proposed framework consistently improves the performance over all four chosen open source LLMs. Further, we also conducted an evaluation with the knowledge source. So the result says here that any knowledge about the entity, be it in the form of the entity name alone or partial knowledge, here in this case, we chose 20% of the knowledge or the full knowledge in general, right? So the result suggests that any form of knowledge helps in improving the performance of these LLMs. Suggests that basically any hint of that particular entity mentioned in the audio helps in solving tasks such as Audiopedia. So, of course, while the full knowledge gives the best result, which is intuitive as well. So, finally, we conclude by saying that we introduced Audiopedia, a speech audio question answering task that requires external knowledge reasoning, and we proposed the three subtasks within Audiopedia, namely s-AQA, m-AQA, and r-AQA. And further, we also proposed a framework, AEL plus CALM framework, that can be adapted to any modern day LLM to solve such tasks as Audiopedia. And our results across four open source LLMs show that our proposed framework improves LLM's performance on knowledge intensive tasks like Audiopedia. So we believe that future LLMs should be able to solve the knowledge intensive tasks like Audiopedia out of the box without the requirement of AEL and additional knowledge augmentation using its own internal knowledge. Thank you. Please visit our project page for the dataset. Thanks.